First of all, I'd like to dedicate this entire series to Igor Kroitor and the entire country of India because, well, we just don't teach semiconductor physics to freshmen in the United States of America. I don't know why. Let me tell you about my setup that I've got right here. I've got my Weston ammeter here. It's a DC ammeter, gonna measure some current for me. Got a battery right here, I got a symbol for it, the positive side's over there. It's a 9 volt. I'll just go ahead and clip this sucker on here so we're ready for all future adventures. And then we can go on to this side of the circuit where I've put a light bulb, and if you take yourself a switch, right here, this is my switch, I'm gonna close the switch, then I will see the light bulb light and the ammeter shows that current's going through. Yay, look at that, physics, cool. And the light bulb is a resistor, so it's shown like a little jaggedy thing right there. Now I'm going to take something, see I've got these two alternate paths, and I'm going to take something that's called a diode. And you probably know, what you probably know about diodes is that if you connect a diode like this, it's got a little bar on it. Can you see that little bar there? It's black. And that says that current can only go one direction and it can go towards the black bar. So the symbol for a diode is actually this. The symbol for a diode is a triangle pointing that way. You want to guess whether current can go to the right or the left based on that picture? Yeah, I would betcha that current can go to the, oh shoot, I was going to put a little switch in here. There's my switch, there. Okay, so current can go to the right in this picture, and that's good because we got a positive side of that battery there and a negative side right there. Current's trying to go to the right. Let's see if it will allow it. We got the light bulb, we got the ammeter. Let's see if current can go to the right when I make that connection. Oh, it can. Awesome, so current can go to the right. Now all I'm gonna do is I'm gonna take this diode and I'm going to switch around its direction. So here we go. I'm going to draw now the direction of the reversed diode, and it goes like that. When I reverse it, I'll put a switch in on this side this time so it doesn't look like it's confusing the diode structure at all. There we go. I'm going to possibly connect a diode the other direction. Here I go. No tricks. I'm just switching it around this direction. Live video right here. Just kidding, this isn't live. And then I connect it. Uh-oh. Something broken? Did I disconnect something? No, let me try switching this around. Ooh, let me show you something really cool. If I switch around the battery, then it will work now, but I'll damage my Weston ammeter. Here's the problem. I just gotta touch it for just a second. See the light bulb? Oh, look at that. Look at that. Current can go the other direction now, but the ammeter, oh, it's really sad. It actually, oh, went too far zero. So I'm gonna switch this around, and I'm gonna switch this around now also. If I switch the ammeter and the diode, then it works again, and now, sorry, if I switch the battery and the diode, that's what I just did, then the ammeter functions properly and everything is cool. So take a chance to look at that circuit that I've drawn right there while I'm cleaning up. I've got myself quite a bit of a mess to clean up, and this is why we talk about diodes, because they are non-linear. You're probably accustomed to thinking about things that have resistance by making a graph of current as a function of voltage. So this is how much you're pushing. Right? Voltage is how much you're trying to squeeze those charges through, and current is what you get. And for things that have a well-defined resistance, we're expecting that the slope of this graph will be a positive linear function, like that, or like, I don't know, could be that or something. We're expecting that as we push harder, we get more flow, and that's reasonable for a lot of things. Linear regimes of springs and all kinds of stuff has slope like that. This guy right here, purple boy, is this high resistance or low resistance? R equals what? And this guy right here, R equals what? Well, let's look at the equation for Ohm's law. If we've got linear relationship between voltage and current, then we've got V is I times some constant R. We could solve this for I over V, which will be the slope of the graph, and I find that I over V is 1 over R. So the one with the greater slope, whoa, has less resistance, and that's reasonable because it looks like I'm getting a whole bunch more current at the same voltage than I would in this case right here. So that means that the purple one will let current flow easily, and the pink one's like, nah, I don't like that so much. All right, so this is a story, ultimately, when we get into a diode. The diode is a story of the interaction of 4 things. It's about thugs, guns, G's, and hoes. And you know what I'm talking, oh, sorry, not G's. E's. thugs, guns, E's, and hoes, and I'll get to how all these play in. A lot of times I don't pronounce my L's very well. This is actually holes, and we'll see how the E's and the holes move throughout a semiconductor region. But before we do that, we need to take a little break and talk about the structure of silicon. Silicon has 4 valence electrons, and as such, this is silicon. It's actually a stale marshmallow. It tastes really bad, but it's really good for physics. Notice that anywhere I set this, I'm going to get 3 points touching the ground. Oh shoot, that one's a little bit off, so I made my angles a little bit off. It's supposed to be a nice tetrahedral shape where we've got a triangle on all sides, and there are 1, 2, 3, 4 sides of this. And silicon does this, germanium does this, and guess what else does this? Carbon. But if carbon does it, carbon is in a diamond form. So we're not going to be using diamond as our semiconductor of choice. We'll probably be talking about silicon or germanium. And you may know from experience that silicon is the overwhelming choice for building computers and other kinds of awesome things like that. Now, the structure of the crystal of silicon will be made up of silicon, 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 silicon. Don't confuse this with silicone. They're not the same thing. Stop saying silicone. No, it's silicon. That's the element. It's the primary ingredient in, for instance, sand. So if you took a big pile of sand and you melted it out and you got just the silicon, not that other junk that's part of sand also, and then you let it form a crystal, it would be like meters long. Wow, and it'd be like this cool drippy looking thing. And it'd be kind of semi-metallic, awesome, beautiful looking. Then you could slice that up and you can make millions of dollars making computer chips. That'd be fun. But here's the structure. We've got this 4 valence electrons, and they form 4 covalent bonds. Boom, 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 boom. But there are other things that could be put into the silicon, and they are, arsenic. Arsenic has 5 valence electrons, 1, 2, 3, 4, 5. It would really prefer to make, well, what would it really like to make? It'd really like to make 5 covalent bonds, but silicon's not going to allow that because the structure of silicon demands just 4. So there will be an extra something floating around. It seems like there'd be a way for this. Well, let's think about that in just a minute. And this guy right here, this guy just has 3 of them, and it's maybe boron, for instance, with 3 valence electrons. Boron could also be put into your silicon structure to make it a little bit different. This topic is called doping. So picture this with me. Excuse me, you're just some run-of-the-mill silicon atomic crystal, for instance, and you got a silicon here, and 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 a silicon here. And of course, this is 3-dimensional and beautiful, but I'm going to smush it all down into a flat plane so that we can do a little bit of talky about it. And you are exactly the same as every other crystalline silicon in the minor leagues, and you got a stagnant batting average, and so your life's kind of going nowhere. So what do? You take arsenic. You put an arsenic atom in here instead of silicon and maybe another one over here. I don't know, let's just focus on one first. And suddenly that arsenic has a totally different valence structure. These silicons, they're gonna be bonded up with a double covalent bond like here, and here, and here, and here, and these guys, etc. But when we get to arsenic, see, arsenic's got 5 valence electrons. It's called tetravalent. That's pretty cool. That means, so all these silicons have 4. You see 1, 2, 3, 4 from this one, and the other 4 electrons that are present in these covalent bonds are from the silicon nearest neighbors to it, in a beautiful structure that looks a heck of a lot like that. But remember, we took an arsenic, and that arsenic has 5 and would prefer to form 5 bonds, but that's not going to happen because there isn't any arsenic near it. What I mean when I say doping is just a tiny bit of arsenic replaces the silicon from time to time. And what we're going to get is we're actually going to get 4 double covalent bonds. But the issue is arsenic's got 1 extra electron that's hanging out right there. So arsenic is considered a donor. Here's that extra electron that's hanging out right there, and it's not in any bonds, and so everybody's really sad about that. Now what's the arsenic gonna do for us? Great question. Arsenic's going to get us a floater. This electron is now going to be free. It's actually in the valence band, and it's not in a bond. So I'll call it a floater, and you might just call it a free electron. Now suddenly, this can conduct. And I want to make an analogy for you of like being full, like a parking garage, being totally full. Here we go. Parking garage, totally full. But if I have an extra electron, that would be digging into here and getting an extra electron and putting it up above, and now see that extra electron can move from place to place because it's not in this band right here. It's in the, it's in the valence band, so it's a free electron that can cause a current to flow. So suddenly, we've got ourselves not just, excuse me, not just a boring covalent structure, but we've got an electron that can hop from atom to atom. And it's very easy for that to happen at room temperature because temperature causes vibrations, and vibrations kick this electron, and so it could go any way you want. Now remember, I was talking about thugs, guns, E's, and hoes, and so what we had was, what about the gun? We could also use the gun right here. Oh, let's say you turn on your gun. And you shoot the silicon. Suddenly the silicon, wow, you could actually kick an electron out of this covalent bond right here. You'd have an electron leave, and then what's left behind? Well, I'll tell you what, it's a place that would like to have an electron, and we're gonna call that a hole. Hole is left behind. Now we don't have, here's what we've got here. We've got, if we put arsenic in this sucker, then we've made N-type silicon. N-type silicon is silicon that has a tendency to be kind of negative because this electron is floating in here. Now, of course, it's not net negative, but it's got negative carriers that are free to move. On the balance, most of the carriers are going to be negative. So let me make the analogy again with the parking garage. If I've got a full parking garage right here, but instead, oh, remember that gun? I was gonna turn that sucker on and hit one of these electrons out of the covalent bonds, and then it shoots up in here into the valence band. That sucker can conduct, and suddenly it'll go like this, and like this, and like this, but only if I've tilted the parking garage. And if there's enough heat for it to jump from hole to hole, I can make it, wait, from spot to spot, I mean, from atom to atom. Another thing that I could do is I could kick this out. Watch this, I kick that electron out of the bonding structure of the silicon, and then if I tilt the garage, that's where my thugs come in. You need some thugs to tilt the garage. If you tilt the garage, then not only does this car move to the left, but guess what happens to this car? It moves to the left also. But look what happened. It didn't really matter that this car moved to the left. What really mattered is that the hole that was here moved to the right. So we're going to talk about holes. See that hole went to the right and the electron went to the left? We're going to talk about holes as if they are real, but they're not. They're just a construct, but it's much easier to talk about the motion of a hole than it is to talk about the motion of one electron, then another electron, then another electron, then another electron. So I'm going to come back to this. Remember we hit this with a ray gun. We kicked an electron out and a hole was left behind. Now what could happen is that hole, if we turn on an electric field, let's put an electric field in with orange. Let's have an electric field pointing this direction. You know, what the heck, in this N-type silicon. If we put on an electric field facing that direction, the electron will want to go this way. That's the force felt on the electron by the electric field, that direction. And the hole, well, the hole will actually want to go that direction because the hole is positive and it will go in the direction of the electric field. Interesting. Now we've got a hole that's moving to the right and an electron that's moving to the left, and we've just invented solar panels. Awesome. We can use those charges that are separating from each other because of the external electric field to actually create electricity. Yes. But we need to get back to doping because we need to understand diodes. So this is N-type silicon when I've got some arsenic in there. I think it's AS. How embarrassing. Arsenic is AS. And the next step is to take boron. And let's say you've got all your silicons, right? I'm just going to do a few of them. Silicon, 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 silicon. And we replace one of them with boron. Here's my doping happening right here. Boron, see, boron's kind of funny. If this is, I'm trying to make p-type silicon. P-type, boron's only got 3. And so if I'm making these bonds, remember I made my bonds in purple, I'm going to make a bond with that silicon, that silicon, that silicon, and that silicon. But we've only got 3 of these dudes right here. There are only 3 valent electrons on boron. That makes it trivalent. So I'm going to make 4 bonds. But the problem is, I don't have enough electrons to satisfy it. I've got 4 from the silicon nearest neighbors, and I've got 3 from the boron. This electron isn't really there. So it's actually a free hole because there's no electron there. That's kind of strange. There is an insufficient number of electrons on the boron. And if that hole moves, see, that hole could move away, another electron could pop into that hole and it could move, then we're left with a free hole that can move through the conduction band. Watch that go. Wow. Fascinating. So the thing is, if we dope silicon, let me start making this a little bit more beautiful here. If we dope silicon, N-type, let's make a little summary. N-type semiconductors have extra electrons, have extra free electrons, and they like it. In fact, they are still neutral, but there are extra built-in holes and extra free electrons, and they prefer to be that way. But p-type is the exact opposite, has extra free holes, not electrons, and they like it. Crazy, crazy. Okay, so holes are given by acceptor impurities. So for instance, arsenic or germanium. And let's see, electrons, free electrons, are given by donor impurities because these guys, these guys donate electrons. And so they're called donor impurities. And we're talking about, for instance, arsenic and what, germanium, yeah. And then you've got these guys that accept electrons, and their acceptor impurities. That's my ray gun turning off. So, for instance, boron for that. Okay, now, the only question we have is what's going to happen if I put some N-type next to some P-type. So that is where we actually get a diode. So I'm going to start with this sheet right here. I've got a whole bunch of extra holes on the left side and a whole bunch of extra electrons on the right side. So if I'm going to put some names to this, I'm going to tell you that this is the P-type silicon, and this is the N-type silicon over here. And actually, I have to remind you that this is not actually how you would do it. You wouldn't get some P-type, get some N-type, and glue them together, because you're going to have oxidation on the surface, and they're going to be crystalline facets that don't line up. What you really need to do is you need to make a block of silicon that somehow has P-type and N-type transition within it. So it needs to be from a single crystal. And you can do that again with the gun. You can actually shoot it a whole bunch with some really interesting, well, not a light gun in that case, but some radiation. You can get it to change. Or you can have a whole bunch of boron on one side and arsenic on the other side and do that chemically while you're forming the crystal. But it has to be done first. But I'm going to pretend, though, for instance, that you could take P-type and set it right next to N-type. Now, immediately, what would happen? The question about what would happen is if you set those guys down then these electrons would see these holes over here and they would actually move over to the left side. And the holes would see the electrons over there. Remember, they're free, and so they'd move over to the other side. So I created this overlay, and I think it would look a lot like that. Now, what that's going to mean is we've actually got, again, a no free carrier zone right there, because the electrons have gone over and met these holes, and we could say that they've recombined, and these electrons have gone over to these holes, and some of these holes have gone over to some of those electrons, and what we've got is, back up. This is neutral. The N-type naturally is neutral, and the P-type naturally is neutral, but the electrons are free to move. There are holes that are built in over here, and there are electrons that are trapped into the covalent structure over here. So, I've got electrons moving over there during the connection, and holes moving over there. So we've actually got a very, very interesting situation. I'm going to get out another pen over here, and I'm going to say, remember we had holes that moved over to the right side? So this side becomes very positive. It's actually got a huge positive charge. And then over on the left side, it becomes very, very negative. And it's actually got a significant negative charge on the left side because all the electrons have run over there to hang out with those holes. And as a consequence, this region is called the depleted region because there are no free carriers. Some people also call it the space charge region because space is really cool. I think there might be another reason for that. Space charge region, this guy right here, the built-in depletion region or the unbiased depletion region. What I mean is I haven't done anything to it. I've simply connected them, and it prefers to make this. Now the issue though is that we've got a negative side and a positive side, and that's going to make an electric field. And the electric field is going to point from the positive to the negative, so the electric field is now to the left. And this is an electric field that is built in by the very structure of P and N next to each other. And the electric field ultimately stops this migration of these electrons coming over to there. You see how this electric field opposes these electrons moving to the left. So some of them won't move. And some of these holes here won't move over to that side. There establishes immediately an equilibrium when there's a p-type next to an n-type, and we have this depleted region where there are no free charge carriers. And the thing is, when there are no free charge carriers, you can't get a current to happen. So our next video is going to discuss what happens if we actually do something to this, but this is a diode before you have begun messing with it at all. We've created a diode, and we actually have extra electrons in the left side, in the p-type, and extra holes, or a shortage of electrons, in the n-type on the right side. And we could talk about the Fermi level, and we could talk about the Boltzmann temperature, but what I want to do very, very, very quickly is talk to you a little bit about the potential difference. If you've got an electric field that's pointing to the left, that means the potential must be decreasing as you go to the left. So I'm going to make a graph of potential as a function of distance. This is electric potential as a function of distance, and it starts out low, and during the depletion region, it's actually changing, and then it becomes high. Sorry, this is kind of a sloppy graph. I was hoping to make this a steady slope here, and then that is causing an electric potential, and that's actually a built-in voltage. So this level between here and here in voltage is called the V built-in. It's a built-in voltage drop that's present inside of a diode. Wow! Pause. There's another video, but we need to take a deep breath.